Let's talk briefly about electromagnetic waves. Typically, electromagnetic waves are characterized by four properties. Their wavelength, which is just the peak-to-peak distance of a wave. So you can either measure it from the sort of 0 point of a wave, like they're doing here. That's one wavelength. Or the other way you can look at it is you can actually measure from the top-to-top distance. So from the highest point here to the highest point there, that's equal to one wavelength. And you can see those are equal. It doesn't matter. It's just the distance from one point of a wave to the identical point on the next wave. That's my wavelength. It's abbreviated with this Greek letter, lambda. We also have the amplitude, which is the height of the wave. So the higher the amplitude, for instance, the brighter a light would be, or if it was a sound wave, the louder the sound. Of course, sound waves aren't electromagnetic waves, but it's the same general principle. So amplitude kind of has to do with brightness in terms of electromagnetic waves. Frequency is a measure of how many waves pass a point within a certain amount of time. So let's say I drew a line here and I had a counter and this wave was moving to the right. I could calculate how many cycles got past that line within a certain period of time. So that's the frequency of the wave. So the frequency units are typically either called hertz, which is abbreviated Hz, or 1 hertz is equal to 1 per second, so 1 cycle per second essentially. So we either refer to it as hertz or in these weird per second units, which are also sometimes written s to the -1. So a little weird, but that's all right. Just recognize frequency units are either hertz, 1 over second, or second to the -1. These are all equivalent. Wavelength units, by the way, that's just a distance, so typically we want to use that in meters. Electromagnetic waves are also characterized by their energy, where energies are measured in joules. So let's look at how we can mathematically look at the relationship between wavelength, frequency, and energy. We're typically not that interested in amplitude, so we're not going to worry about that. We're just going to worry about how these three pieces are connected. And we can use two simple equations to interconvert between them. So here are main relationships for electromagnetic waves. First of all, we can relate wavelength, right? That's this piece here, the Greek letter lambda, to our frequency. So this is a Greek letter called nu. I don't know why we call it that. Sometimes you'll see it just given by an F, but a lot of textbooks or other books call it nu, and it's just this Greek letter. But we can see that there's a really simple relationship. If you multiply the wavelength, measured in meters, and the frequency, measured in hertz, or 1 per second, when you multiply those together, those give you the speed of light, 3 times 10 to the 8th meters per second. So we call it the speed of light, but really this refers to any electromagnetic radiation, and so that's why it's going to work no matter what the wavelength is. If it's visible light or not, this relationship is still going to be true. So C, speed of light, is equal to wavelength times frequency. Now once you have the frequency, you can go down here and plug it into this second equation where you can use this to calculate the energy of the light. And here H is just a different constant. We call it Planck's constant after the person who measured this for the first time. And it's this long number here, 6.626 times 10 to the -34 joules times seconds. But the basic idea is once you have frequency, you just multiply these guys together and it gives you the energy. So let's look at an easy example. What is the frequency and energy of light that has a wavelength of 532 nanometers? So first, I'm just going to write in my symbols because they're really easy to get mixed up. Frequency is this weird V-looking thing that we call nu, so that's my frequency. Energy, of course, is E, and wavelength is this odd-looking Greek symbol called lambda. So the only one we have right now is that lambda is equal to 532 nanometers. And we're looking for frequency and we're looking for energy. And we've been provided with two equations. So before we can use this one, we're going to have to figure out what the frequency is. So let's start with this one over here. So I know that C is equal to wavelength times frequency. I'm going to go ahead and rearrange this and solve for the frequency, which is what I need. Frequency is equal to C over lambda. So I just divided both sides here by lambda, cancels out on that side, and I get the frequency is equal to c over lambda. Now, one difficulty is that if we look at our constant c, so that would always be given to us, it's 3.00 times 10 to the 8th meters per second. My constant c has units of meters, but my wavelength is in nanometers. So not surprisingly, I'm just going to need to do a little conversion. So I'm going to need to take my nanometers and I'm going to need to turn that into meters. So I'm just going to sneak it up here because I don't have that much room. So I have 532 nanometers. So we're going to get rid of the nanometers and turn it into meters. It's a simple relationship. We look it up on our metric prefix chart. 1 nanometer is equal to 10 to the negative 9 meters. So our nanometers cancel, and we get 5.32 times 10 to the negative 7 meters. So that's just like any other simple conversion. So now we can take this and plug it in here. So my frequency is equal to c, which is 3.00 times 10 to the 8th meters per second, over my wavelength, which is 5.32 times 10 to the negative 7 meters. So my meters cancel, and I end up with these weird units of per second, which is also called a hertz, and that's what I would expect for frequency. So I just do my division here, and I get a pretty big number, 5.64 times 10 to the 14. So the frequency is 5.64 times 10 to the 14th hertz. So now that I've answered that, I can go on, check, I know that, I need to find my energy. Well, now that we have frequency, this is really easy. Energy is just equal to h, which is a constant. H is equal to 6.626 times 10 to the negative 34 joules times seconds. So that's always a constant. That'll be given to us times the frequency that we just measured. Or, well, calculated. 5.64 times 10 to the 14, and it has these units of hertz. Sneak that in there. So we're just going to multiply these. The seconds and the hertz cancel, because hertz is a 1 per second. So we did seconds times our hertz is a 1 divided by seconds. So these cancel and just go away, essentially. So all we're left with is joules, which is what we would expect for energy. So we do this times this, and we get 3.74 times 10 to the negative 19 joules. So once we have the frequency, we can just plug it into our second equation, and we can also get the energy. So our frequency was 5.64 times 10 to the 14th hertz. Our energy was 3.74 times 10 to the negative 19 joules. We should also be able to go backwards. If I gave you an energy, you could plug it in here to get the frequency, and then plug it in here to get the wavelength. But the general idea is, like many of our problems, making sure the units match. So you always want your wavelength to be in meters, always want your frequency to be in hertz, and always want your energy to be in joules. And as long as you make sure of that, I'll give us the constants we need to plug in. You should just be able to plug in and solve for the one piece you do not have.